Hi, pre-calculus friends. We are looking at section 3.2 and we're talking about families of graphs. We only have one vocabulary word and that is parent graph. And parent graph, honestly, could be any graph that we're going to riff on. All right. Any graph of a function that we're going to manipulate or that we want to consider for manipulation. So that manipulation could be lifting, translating up, down, left, right, compressing vertically, reflecting over the horizontal axis. Any of those graphs that we want to do something like that to is considered a parent graph. It's almost like the starting point, all right? So what I want you to do, let me go ahead and make this a little bit larger, is just make sure you know each of these graphs. Each of these can be a parent graph for us. So if you look y equals 0, some of its children, just to continue with the kind of analogistic talk, could be y equals 3. Well, it's related to this graph, but we know that that is translated 3 units up. Y equals 3 would be considered kind of a child graph to this particular one. And similarly, we can talk about y equals x being a parent graph, and I can do some cool things like say, well, what about y equals 2x? And see that that gives me the same kind of a graph, but the slope is indeed more steep, and therefore we get something different. So this would be a child graph to that in a sense. All right, so y equals x squared, we've got the parabola. Any polynomial function in essence could be considered a parent graph. And so, it's not limited to y equals x squared or y equals x cubed. So knowing these will be really helpful in our having it in our arsenal of tools to use to help us graph. Come down here, the square root function. It looks like half of a parabola on its side because literally that's kind of what it is. If I put x in, I'm taking the square root of it to figure out what the y value is. Here we have the absolute value function. The absolute value function is going to be a function that is going to give us a v. It's like a line, but then since it has to be positive, it's kind of broken up there. And this guy we'd be translating around and adjusting it in a number of ways. This is the greatest integer function. If we haven't talked about it together, let's make some time to do so. It is basically saying, what is the greatest integer that is less than or equal to this x value? And if you thought through that, you'd see that we'd end up with these kind of like lollipops, these step. It's really called a step function because it looks just like that. And so this is one we want to memorize. And then finally, a rational function where we have 1 over x, which gives us this hyperbola kind of on a diagonal in a sense. And these will be the ones that we will play with in this chapter. So let's go ahead and take a look at some examples. So this example 1 is asking us to compare the graph of f of x equaling the absolute value of x and g of x equaling negative the absolute value of x. So I'm going to graph this first one. Let me highlight it. And I'm going to graph it right there. We've seen this as one of the parent graphs. It's basically the y equals x line, and then instead of it going down, it goes up because we're dealing with the absolute value. Let's make that look a little bit neater. Something like that is what we'd have. So this is that first graph. And the question is, what happens here? You might already be kind of checking it out and understanding what's going on is the idea that in every value that y is, because we know that these f of x and g of x is another way of referring to y, every value that y is for f of x, we will have the exact opposite for g of x because it will all be negative. Does that kind of make sense? So everything is reflected over the x-axis. And this is just one example of this kind of a reflection. Let me show you another. So I'm over here in Desmos and I've graphed, I hope you can see my whole screen. I've graphed y equals the absolute value of x, and then we'll just put here, we confirm that y is equal to negative the absolute value of x gives us that v situation. But let's see, I'm going to erase those guys. Let's see what happens if we try the same thing on a different function like y equals x squared. Notice when I throw the negative in front of it, it reflects over the x-axis. So this is something that we can kind of feel comfortable will always happen. Here's a function I like to use that we're not familiar with yet. It's the sine function. You'll notice that the same thing happens with the sine function. It refers to trig that you did in geometry, and we'll talk about it in more detail this year. So look at this, y is equal to sine of x, y is equal to negative sine of x. Again, no matter the function, no matter the f of x value, we are going to get that same reflection over the x-axis when we throw a negative in front of our function. So what I've done here, let's take a look at example 2. It says use the parent graph y is equal to the square root of x to sketch the graph of each function. So I started off with the parent graph here, y equals square root of x, just to give us a guideline as we look at some of these other functions. So let's go ahead and get started. I'm going to highlight this first one. Well, maybe I'll just kind of do a little circle in black highlighter, whatever that is. And so we've got y is equal to the square root of x plus 2. So what happens when we have the function and then we add 2 to it? What this says is that whatever we got for y, we're just going to add 2 to that value. So remember, y was 0 here when we just had y is equal to the square root of x rather. Add 2 to that, we're at 2. Y is equal to 1 here. Add 2 to that, we're at 3. Y is equal to, where are we at? 1, 2, 3, 4. At 4 in the original graph, y is equal to 2. If I add 2 to that, I'm all the way up at 4. Are you guys seeing what's happening? 1, 2, 3, 4. Make sure I'm at the right place. And at 9, we're at 3. Add 2 to that, I'll be at 5. So I should be right about here. All right, so what we see is we have this. Let me make it better. Hold on. We have this graph like this. And this is going to be y is equal to the square root of x plus 2. And so you see how we use the parent graph in order to shift this graph up. And so now what we want to do is kind of regularize a law. That's not a good word, but you know what I'm saying. We want to recognize that this 2, and if this were a positive 3, we would lift up 3. If this were a minus 4, we would go down 4. This is going to translate up and down. Okay, so let's take a look at part B. What we see here on part B is that there is a number that's being added, well, in this case, subtracted directly from x. This is a different scenario than this one over here. This number is actually, this x value is actually being subtracted from before we actually take the square root of it, and that is going to have a different effect on our graph. So I'm going to graph this one in green. And so what I want to ask you is figure out what's going to make this graph 0, like what value of x would make this 0. And if you do that, you'll see what happens. So we're going to have the same parent function, but we're going to slide it 4 units to the right. Because notice, what happened once when x was equal to 0 is now happening when x is equal to positive 4, because that's what will make the graph 0. And so everything is going to happen, in a sense, 4 units above. So here, remember, we started at 0, then we went to 1. Here we're going to start at the 0, and then we'll go up 1. Is that making sense, guys? I hope so. And then over here, we're going to go over. So remember here we went over 1, 2, 3, 4 and up 2. We're going to do the same thing. 1, 2, 3, 4 and up 2. And you're going to see that these points will bear out. It will make perfect sense. Even if you were to use a table, what we're trying to do is give ourselves the opportunity not to use a table, right? So here's what I want you to observe. This number that is acting directly on x, either adding or subtracting, is going to translate our graph left or right, depending on whether or not we have a plus or a minus sign here. So this minus 4 actually shifted it to the right. A lot of students get confused with this. And then this, if we had a plus sign here, that was shifted to the left, because you would think, what would make this function 0 or start in the same 0 place? And if this were a plus 4 per se, then we would have to start at -4. So it's almost counterintuitive, but if you think about 0 values, it makes perfect sense. All right, so now in this example here, I want to drag my graph down because I like graphing on the same pair of axes all the time because it's really, really helpful and being able to compare our graphs. So I'm going to slide that down there. Not too bad. Had a little bit of a hiccup. All right, so what we'll do at this point, that wasn't the goal. What we'll do at this point is we're going to graph this one here. And this graph, let's say we do it in red, is going to have two translations. If you notice, one translation will be down and the other translation will be to the, do you remember from our last conversation? It's going to be to the left, 3 units. And so that's all that's happening. Nothing else is changing in this graph. So I'm going to quickly do that one. It's going to still be the parent graph, but shifted to this new location. So again, I'm translating 1 unit down and 3 units back. 1, 2, 3. So my graph is going to start here. So this is kind of like my 0 line. I go up 1 over 1. I went out 1, 2, 3. Let's see. Let's put it here. I went out. I realized that I'm a little bit off. I'm going to do it one more time. So I went down 1, back 3. I'm starting here, and up 1 over 1 will put me here, right? So that's that same beginning movement that we see. And now I'm going to go over 4 and up 2. And then so my graph is going to do something like this. There we go. Not too bad. All right, so that's what's happening here. So we have 2 translations. We have a translation down, and then we have a translation to the left, 3 units. There we go. And that's all we need to do when we're graphing these types of parent graphs and checking out what happens as we shift them around. So here in example 3, we're going to graph each function, and then we're going to describe how it's related to the parent graph. Well, that sounds great, but we need to kind of figure out what the parent graph is. And so in this case, the parent graph, if you remember, would be that greatest integer function. Call it a lollipop function because it looks like a bunch of lollipops sitting on its side. Or we could even call it a step function, which is probably the more mathematically appropriate way of referring to it. So like usual, I like to graph the parent graph in gray so it doesn't take up a lot of visual space for us and we can kind of think through. So if you remember, I'm going to try to draw this a little bit neatly off camera. Okay, so that's as neat as I could get it for this particular moment. So let's go ahead and call this like y equals the greatest integer of x. And remember, we're basically mapping y with the integer that x is either equal to the greatest integer that is either less than or equal to x. Sit there and think about that for a minute because it takes me a minute to say, yeah, that makes sense. All right, and so sometimes I'll say, you know how when you're a little kid, you're like, I'm 1.5. This function doesn't care about that. So if a child is 0, the child is 0. If the child is a half year, the child is still 0. If the child is the day before their first birthday, the child is still 0 until the child has the first birthday. Then we say the child is 1. And all the way up until the second birthday, we will continue to assign the child the age of 1 until they are 2. Are you guys with me? Hence these open circles and these dots. Okay, so think about that and let's think about how this graph will relate to how this graph will affect the relationship between the parent graph and this one here. So look at this. G of x is equal to 2 times the greatest integer function. So what this says is that, okay, I'm just going to multiply each of the values for y by 2 in order to get the new values. So 0 times 2 is 0. So that's going to be like that. That's going to stay. But this next one, watch this. When I multiply 1 times 2, it's going to pop all the way up here. And we're going to get that situation. What's going to happen here? It's going to pop all the way up here. Everything is going to be, and I'm going to use the term that I want you guys to think about, everything is going to be vertically stretched. We're going to get a vertical stretch right now as we compare this original graph, the gray graph, with the pink graph. I'm going to show you, let me see if I can grab a Desmos situation real quick so you can see. So you remember we were playing around with this graph, right? We're looking at this function that we're not really familiar with, y is equal to the 2 times sine of x. What happens when I throw a 2? When I throw a 2 right next to it, when I multiply it, what I've done is I have amplified the graph. That's language that we'll use a little bit later. But what I've done is I've done a vertical stretch. And so what I want you to get from this particular example is when you multiply your function by a value, you're going to get either a vertical stretch or what we're going to see in a moment, a vertical compression. All right, so that causes a vertical stretch or compression. Now, if we look in this particular graph, you will see a couple things happening, probably too many for me to graph by hand right now. I might actually just pull up Desmos to get a little bit of help for us. But first thing we see is that we have a coefficient, and that coefficient is 0.5. And I know we haven't discussed this, but whenever we have a coefficient of our entire function that is less than 1, or somewhere between 0 and 1 is really what I want to say, we're going to get a compression. Now, I know this negative is having an effect in your mind. You're like, well, what's going on? Well, let's kind of play this whole idea out. First thing we know, well, we already know a couple things. We know that this -4 is going to cause a vertical shift or a translation down. We get that. This coefficient, like this one up here, is going to cause some kind of a stretch or compression, and because we are dealing with 0.5, it's going to cause a compression. So we're going to shrink the graph down. So this whole thing is going to shrink down a bit. The next thing we're going to do is actually reflect it over. Do you remember what the negative way back in the beginning of the lesson does? The negative is going to give us a reflection over the x-axis. So our graph, and I'm going to just kind of give you an idea, is going to be shifted down in this direction. So we're going to have something like this, kind of squashed like that. And then, so a little bit compressed, that's a vertical compression. Also, I'm showing that it's shifted in the other direction, meaning it is reflected over the x-axis. And then finally, from there, it would be shifted down 4 units. Now, because this isn't exact or pretty, I'm going to employ Desmos to help us out a little bit here. And it might be nice for you to be able to see how to use Desmos to actually get a step function. So when we're graphing a step function in Desmos, we would go over to functions. That's after pulling up the keyboard. We go over the functions and we go to miscellaneous, and you'll see nothing that looks like what we've talked about, but there's this word floor, and that's the floor function. So we're going to do the floor function of x. It gives us that function, but it's a little bit different because it doesn't have the open circles. In fact, its value is slightly different, and technically I would say it's not a function because it would fail the vertical line test. Look, x has 2 different values, but we'll stop playing around with this and use it for what it's worth. So let me make this into a black function so we can use that as the kind of the background, and now we'll consider the equation that we had before. So we had a couple things going on. One is we had this function was multiplied by 0.5, and we see when we do that we get a vertical compression. So I'll go kind of got smaller, okay? Then we actually had a negative value here. So look, there's that reflection across the x-axis. And finally, I'm going to subtract 4, and boom, it gets slid down a little bit. And I know this is like a whole lot going on, but you guys see I was kind of right? You know what I mean? I'm going to go flip back to see how okay, it's not as pretty, but you get the idea. So we had 3 things operating on that function. 1, we compressed it with that coefficient of 0.5. Next, we flipped it over the x-axis with that negative. And then finally, we shifted the whole thing down by subtracting 0.4. All right? Well, not 0.4, but by subtracting 4. My bad. So example 4 is kind of like interesting. We can kind of talk about rules here, but what I want you to do while we work on this together is I want you to be thinking about not really a rule. What did she say to do when we had this? But what does it actually mean? How is it going to affect our parent graph? So the first graph, observe the graph of each function, describe how the graphs in part B relate for the graph in part C and relate to part A. Let me read that again because that sounds crazy. Describe how the graphs in part B and C relate to the graph in part A. So we are starting off with a parent function. And I know this isn't our typical parent function. Typically, it's like very basic, but anything can be a parent function. So f of x is what we're going to riff on in all of these other examples. So if you look at this, you can see, oh, this is definitely a parabola. It's got that x squared situation. And then we can see that the vertex of the parabola is shifted. This is vertex form. So we know that we are moving 2 spaces to the right, 1, 2, and 3 spaces down, 1, 2, 3, for a vertex point here. And if you remember anything about parabolas from last year or previous year, you'll know that they have a very distinct shape when our a value, which is 1 here, is 1. So it goes out 1, out 2, up 4, out 3, up 9, because we're squaring each of these values. So I'm just going to do kind of a little number like this. I'm not being particularly perfect with it at this time, but I just want us to have an idea of what it's going to look like. And we can use Desmos to kind of tighten it up in a moment. So what happens if I take this same function and I'm to put absolute values around the entire function? What does that mean? Meaning I want no y values that are negative. That's what this is saying. All the y values should be positive. That which were going to be negative needs to be reverted to its positive form. So I'm going to highlight this for us. And let's see, this is a good enough color. I'm going to highlight this and I'm going to graph. So everything else would be the same. As long as y is positive, everything would be the same. But as soon as y is negative, we're going to get kind of a rebellion. And you'll see that everything will flip on the opposite side of the x-axis. My pen is acting up, but you guys see what this is. We get this weird thing that happens. It pops up. And this does not look like a parabola at all, but this is how we have to process through what's happening when we do these alterations on parent graphs. I hope that made sense. I hope that made sense. You guys will let me know. All right, let's try another one. So this last one, and this will be our last example for this section, and we can talk in person if you have any other questions. So let's take a look at this one. Instead of taking the absolute value of the entire function, we're just taking the absolute value of x. What this means, if I think about the original, is that I'm never actually putting a negative x into the equation. I'm only putting a positive x into the equation. I'm only putting positive values because no matter what I try, I'm always going to get a positive version of that x value. So what does that mean for our original graph? So I'm going to erase all this stuff. I'm going to use this orange color to show you what it looks like. And so check this out. So remember, anything that happens on the positive side of x is also going to, so let me highlight that. This is all affirmed. All of these values would be cool. But as soon as I go into the negative realm, my function's not going to deal with the negative version of that x. It's going to deal with the positive version of the x. And so look at what I get. I get like this. All right, let me try it again. I get like this funky W-like situation, right? So where there is a mirrored reflection, it's mirrored over the y-axis, whereas last time we had like kind of a flip or a mirroring over the x-axis. Kind of a mirroring, not exactly, more of a flip. Does that make sense, guys? I hope so. I'm going to skip the last example because it's a little bit out of the realm of what we're talking about, and I am not super inclined to explain it the way the text did. The gist of the problem is you're given some points. You realize by plotting those points that they fall in a parabolic arch, and you're now to use this information to find the equation of a parabola that is related to this, or a quadratic equation. To me, it's a little bit out of the realm of parent graph, so I'm not going to touch it right now. However, I would like to touch it when we talk in person. So remind me of this example so we can find an efficient way to handle it. Other than that, I've enjoyed talking to you. Let me know if you have any questions, and I will talk to you soon. Take care. Bye-bye.